Good evening everyone, good evening. I welcome you all again to JEE Enthuse. I hope you guys are doing great, having a good time. So people, first of all, before starting the session, you can let me know in the chats if I'm audible and visible to everyone. You can just let me know in the chats if I'm audible and visible to everyone. Hello Anil, hi Ashwarya, hi Chitra. Welcome back everyone, welcome back. Hello Akshay. Welcome back. Just give me some green signal from the chats if I'm audible and visible to everyone. Hello Irtika, welcome, walaikum salam. Let me know fast in the chats, guys. Chemical equilibrium will be done day after tomorrow, okay? Yeah? Dinesh, I have to take care of both the things, class 11th and class 12th people as well, right? So for 2 days I was taking the session for chemical equilibrium. Now it's going to be the time for class 12th students for the electrochemistry, yeah? Okay? Yes, Anzar, chemical kinetics will be done too. You just wait for it. Every single thing will be done. You just give me some green signal in the chats if I'm audible and visible to you so that I can start the session directly without wasting a lot of your time. Yes? Exactly, this is electrochemistry part 1. Exactly, I'm going to start the electrochemistry from the scratch. Right? Okay, so people, let's get going. Let's get started with the chapter electrochemistry. And what all things I'm going to discuss in the tonight's session, I'll be talking about something called as electrochemical cells. We'll be discussing about the galvanic cell. We'll be discussing about the Daniell cell, its construction, its working in detail, right? So before starting the session, the ones who have just joined in, let me introduce myself. Well people, my name is Wassim and I'm your chemistry master teacher writer on this JEE Enthuse channel, yeah? The ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this JEE Enthuse channel, right? Yes, Arun, electrochemistry is going to take 7 sessions. It is going to get done and dusted in just 7 sessions, okay? Amplifier equilibrium will be there day after tomorrow, yeah? Perfect. So people, you can let me know in the chats if you guys are super duper excited for the tonight's session as well, yeah? Just let me know in the chats if you guys are super duper excited so that I can start the session directly, right? Let me know in the chats. Wonderful. Perfect guys, perfect. So let's get going. Let's get started with the chapter called as electrochemistry, yeah? One of the most important chapters of your class 12th chemistry, right? So people, the first topic which we are going to cover in the tonight's session is something called as electrochemical cell. Electrochemical cell. What are electrochemical cells all about? What are electrochemical cells all about? Okay. Well people, electrochemical cells are the ones which are going to convert either chemical energy into the electrical energy or electrical energy into the chemical energy, right? Okay. Electrochemical cells, these are basically the cells, these are the devices. These are the devices which are going to convert, either chemical energy into the electrical energy or electrical energy into the chemical energy, right? So any device, any cell which converts either chemical energy into electrical energy or electrical energy into chemical energy is something which I call as electrochemical cell, right? Well people, this electrochemical cell, it is actually of 2 types. It's actually of two types. The first type, which I'm going to discuss in the tonight's session, is what I call as galvanic cell. This is the first type of electrochemical cell, okay? And this galvanic cell, let me tell you, it is going to convert chemical energy into the electrical energy. It's going to convert chemical energy into the electrical energy. Point number one. We are going to see in detail how chemical energy will get converted into electrical energy through this galvanic cell. Point number one. Point number two. In this galvanic cell, some reactions will happen on its own. There will be some spontaneous chemical reactions which will lead to the generation of current, right? In case of galvanic cell, you will see in some time, there will be some spontaneous cell reactions going on, right? Due to which current is generated, which we are going to see in some time, right? In this galvanic cell, we are going to use two electrodes. One is called as anode, another one is called as cathode. Well, let me tell you exactly. The rod of the anode in case of galvanic cell is going to carry negative charge, and the rod of the cathode in galvanic cell is going to carry positive charge. Why they are going to carry positive and negative charge? That's also something which we'll be discussing in detail, right? Yes. So let's get going. Let's get to know exactly the construction, the working of this galvanic cell. Let's see exactly how it's going to convert chemical energy into electrical energy. Let's see exactly what kind of spontaneous cell reactions take place in this cell, right? Let's see exactly how these electrodes are connected, right? How these electrodes are connected in case of the galvanic cell, right? So my topic of tonight's discussion is going to be all about the galvanic cell. It's going to be all about the galvanic cell, yeah? And the common example of the galvanic cell, which I'll be taking right here, is the Daniell cell. This is the common example of the galvanic cell, which is what we call as the Daniell cell, right? Now, before entering into this topic, let me give you some basic idea of certain things, right? What is that basic idea? Have a look. Let's say I'm taking a reaction as A2, a general reaction I'm taking, A2 plus B2. It gives, for example, 2 times A positive plus 2 times B negative. This is the general reaction which I'm taking, yeah? Let's assume this A and B right here are present in their standard states, in their elemental states. And we know when the element is present in its standard state, its elemental state, its oxidation state is taken to be 0, right? So oxidation state of A and B over here is going to be 0. Point number one. Point number two. The charge present on this A right here is +1. So this +1 is the oxidation state of A over here. This -1 is the oxidation state of B over here, right? See, can I say the oxidation state of A is increasing from 0 to +1, right? Let me tell you, increase in the oxidation state of an element is something which we call as oxidation. So I'll say this A2 undergoes oxidation over here. Similarly, let me tell you, decrease in the oxidation state of an element. As you can see, 0 to -1. Decrease in the oxidation state of an element is something which we call as a reduction. So I can say this B2 undergoes reduction in this process. In short, what I want you guys to remember, increase in the oxidation state is what we call as oxidation. Decrease in the oxidation state is what we call as a reduction, right? And any substance which undergoes oxidation will be termed as the reducing agent. And the one which undergoes reduction, that's something which we call as oxidizing agent. I'm sure every one of you will be knowing this, yeah? First important basic thing, what is meant by oxidation, what is meant by reduction, right? Now, second point, I did not start the galvanic cell yet. I'm just making your basics a bit clear first, yeah? If I ask you what electrode is all about, what is meant by the term electrode, how this electrode is formed. See guys, how this electrode is formed. What is this electrode? See guys, have a look. Let's assume I'm taking a rod. Let's assume this is a metal rod which is made up of some metal M, right? It's a rod of some metal M over here, right? What I'm doing over here, I'm taking one container, and in this container I'm going to keep the ions of the same metal of which the rod is made. In this container I'm keeping the ions of the same metal of which the rod is made. Let's assume I'm keeping Mn positive ions in this container. Let's assume I'm keeping Mn positive in this container. Whenever you see such kind of a setup in which a rod is dipped into its own ions, whenever you see such kind of a setup in which a rod is dipped into its own ions, you call this setup as electrode. This setup is something which we call as electrode. Right? For example, I need to make zinc electrode. What I'll be doing? I'll be taking zinc rod. This is the rod which is made up of zinc. I'll be introducing the zinc rod into the solution which contains the ions of zinc. And what are the ions of zinc? Zn di positives. Let's assume in this container there are Zn di positive ions. And in these Zn di positive ions, you have introduced the zinc rod, right? This complete setup, the system is something which I'll be calling as zinc electrode. Let's assume I need to make copper electrode. I'll be taking the copper rod. This is the copper rod which I've taken. I'm introducing this copper rod into the solution which contains the ions of copper. Let's assume there are some Cu di positive ions in this container. I'll be calling this setup in which the rod is dipped into its own ions, in which the rod is introduced into its own ions. I'll be calling this setup as the electrode. And which electrode this is? This is the copper electrode, right? Okay. I'm sure the term electrode is clear to you. Yeah? Now let's exactly see the construction working of the Daniell cell which I'm going to show to you, right? The first thing, if I compare two elements, zinc and copper, I'm comparing these two elements, zinc and copper, right? I'm comparing two elements, zinc and copper. Let me tell you, zinc is considered to be more electropositive than copper. Zinc is considered to be more electropositive than copper, right? Copper comparatively is considered as less electropositive. The one which will be more electropositive, that is the one which will be having the tendency to lose electrons. So this zinc will have the tendency to lose electrons. So this zinc will undergo oxidation. That means this copper will undergo reduction. Right? And let me tell you, oxidation always takes place at anode and reduction always takes place at cathode. So basically in Daniell cell, which is the common example of the galvanic cell, I'm going to use two electrodes. One is of zinc, one is of copper. And zinc electrode is going to behave like the anode and copper electrode is going to behave like the cathode, right? In case of the Daniell cell, I'm going to use two electrodes. One is zinc, one is copper, right? Zinc electrode is going to behave like the anode and copper electrode is going to behave like the cathode, right? Let's exactly see how this cell is made, what is going to be its construction, what is going to be its working, right? Yes, first thing I want you guys to remember, in case of your Daniell cell, your zinc electrode will be behaving like the anode and the copper electrode will be behaving like the cathode, right? Let's now see the construction of this Daniell cell and working of this Daniell cell in detail, yeah? Have a look, guys. Have a look properly what I'm going to talk about. This is the container which I'm taking. In this container, I'm keeping a strong electrolyte. What is that strong electrolyte? I'm, for example, keeping zinc sulfate into this container, which is a strong electrolyte. And this zinc sulfate, if it is a strong electrolyte, it would have got converted into Zn di positive aqueous ions, right? And with this, you'll be having SO4 di negative aqueous ions. Right? So I've taken strong electrolyte ZnSO4 in the container which have got dissociated into its ions, Zn di positive, SO4 di negative. And currently I'm assuming in this solution there are equal number of Zn di positives and SO4 di negatives. Currently I'm assuming there are equal number of Zn di positives and SO4 di negatives into this container, due to which this solution currently is electrically neutral, right? Now what I'll be doing, I'll be introducing a zinc rod into this container. This is the zinc rod which I've introduced into this container, right? This is the zinc rod which I've introduced. Correct? So if it is the zinc rod which I've introduced into this container, can I say I have got a rod introduced into a solution containing its own ions? Definitely. Should I be calling this as the zinc electrode? Absolutely, I'll be calling this as the zinc electrode. So this is the zinc electrode which I've taken. Similarly, let me take one more container. This is one more container which I have. And in this container, I'm going to keep one more strong electrolyte. And which electrolyte am I going to keep? I'm going to keep CuSO4. CuSO4 is a strong electrolyte. It would have got converted into its ions, and its ions will be Cu di positive aqueous plus SO4 di negative aqueous, right? And currently, in this solution, there will be equal number of cations and anions, which makes this solution overall neutral. And in this solution, I'm going to introduce copper rod. This is the copper rod which I've introduced into the solution. This is the copper rod which I've introduced into this solution. So can I say I have got the rod which is introduced into the solution containing its own ions? Absolutely. So this setup I'm calling as the electrode, and this electrode is basically the copper electrode, right? So I took two electrodes. One is zinc, one is copper. In case of the Daniell cell, correct? Now I'm going to connect them externally by means of a voltmeter. I've connected them externally by means of a voltmeter, right? And over here, what I'm going to do is, internally, how am I going to connect them? I'm going to put an inverted U-type tube over here. I'm going to put an inverted U-type tube over here. This U-type tube, what does it contain exactly? This U-type tube, it contains a jelly-like paste. It contains a jelly-like paste. And what is that jelly-like paste? You'll get the idea in some time. Over here, I'm keeping two cotton balls. This is one cotton ball which I'm keeping on this side of the inverted U tube. This one more cotton ball which I'm keeping on this side of the inverted U-type tube, right? Now, inside this, what I'm going to do? I'm going to take an electrolyte, that is something which I call as inert electrolyte. What is inert electrolyte? You'll get the idea in some time, right? I'm going to take an inert electrolyte like K2SO4, and I'm going to mix it with gelatin or agar-agar, right? And when I'll be mixing these two, I'll be getting a jelly-like paste. I'll be getting a jelly-like paste, and that jelly-like paste containing the inert electrolyte contains the ions of the inert electrolyte containing K positives and SO4 di negatives. I'm going to introduce into the salt bridge, into this inverted U-type tube. This inverted U-type tube which contains this jelly-like paste, right? Which contains this jelly-like paste, okay? This inverted U-type tube is something which I'll be calling a salt bridge. So it's something which I call a salt bridge, right? And in this salt bridge, what do we have? We have got the ions. Which ions? K positive ions as well as SO4 di negative ions, right? This is first of all the setup of this galvanics, of this Daniell cell, right? Now guys, understand. In this Daniell cell, as I told you, your zinc electrode is going to behave like the anode, and this copper electrode is going to behave like the cathode. And remember, at anode always oxidation takes place, and at cathode always reduction takes place. Okay? So first of all, when I'll connect these two cells, when I'll connect these two electrodes, right? Just a second, let me just make it clear to you. This is the cotton ball over here. This is the salt bridge, right? This is the salt bridge. Now it must be visible to you properly, right? Just a second. Okay. Now people, when I'll introduce the salt bridge over here in the two solutions, right? See, this circuit, it's externally connected as well as internally connected. This circuit is externally connected as well as internally connected. What is going to happen? When I'm going to connect these two electrodes by means of salt bridge and by means of the voltmeter externally, what is going to happen? At anode, oxidation is going to take place, and at cathode, reduction is going to take place. Yes? So at anode, when I'm going to connect these two electrodes internally as well as externally, at anode, oxidation is going to take place. Oxidation means loss of electrons, and this loss of electrons is happening at the anode, right? At anode, oxidations take place. Oxidation is going to take place. Oxidation of which atom is going to take place? See, this rod is basically made up of zinc atoms, right? So the zinc atoms of which a rod is made up of, the zinc atoms of which rod is made up of, right? These zinc atoms will undergo oxidation, will get converted into Zn dye positive aqueous solutions, and with this you get 2 electrons as well. So the atoms of which rod is made up of, that is zinc, it has undergone oxidation, got converted into Zn dye positive, and with this you get 2 electrons. This Zn dye positive, it is going to enter into the solution. The solution initially was overall neutral because there were equal number of Zn dye positives and SO4 dye negatives. Now, due to the oxidation of zinc atom from the rod, zinc atom got converted to Zn dye positive. That Zn dye positive enters into the solution, due to which there will be the extra Zn dye positive in the solution, due to which the solution gets the positive charge. And these electrons, these are basically accumulated on the rod. These electrons are basically accumulated on the rod. Since electrons carry negative charge, that is why this anode rod over here is going to carry the negative charge. As I told you in the beginning itself, right? I told you in the beginning itself. The rod of the anode in case of Daniell cell, in case of galvanic cell, is going to have the negative charge, right? Okay. Now guys, due to the oxidation of one zinc atom, 2 electrons got accumulated on the rod. Due to the oxidation of one more zinc atom from the rod, I'll say 2 more electrons will be accumulated on the rod. Similarly, due to the oxidation of more and more zinc atoms from the rod, you'll say electrons will start getting accumulated on the rod, due to which this rod gets the negative charge. Yeah? Right? Okay. And due to the oxidation of the zinc atoms of which this rod is made, continuously Zn dye positives will keep on entering into the solution. Continuously Zn dye positives will keep on entering into the solution. Right? Yes. Due to which the intensity of this positive charge will keep on increasing. Right? Now understand. This is something which is happening at anode. Now what will be happening at cathode? At cathode, we know reduction takes place. Reduction means gain of electrons. Reduction means gain of electrons. In this solution, there are 2 types of ions. Cu dye positive, SO4 dye negative. The solution right now is electrically neutral. Right? The solution right now is electrically neutral. There are 2 types of ions, Cu dye positive, SO4 dye negative. Out of these 2 ions, Cu dye positive needs electrons. It is electron deficient. It is electron deficient. So this Cu dye positive, which is in the solution, it is going to collide with the rod. Cu dye positive aqueous, which is in the solution, it's going to collide with the rod, and it will take 2 electrons from the rod and will get converted into Cu solid. Since the Cu dye positive, which was in the solution, it is taking electrons from the rod. It is snatching electrons from the rod. That's why this rod carries a positive charge. Because from this rod, electrons are to be taken out, right? That's why this rod carries the positive charge, which I had told you in the beginning. The rod of the cathode, in case of galvanic cell, it carries the positive charge, right? I'm sure it's clear till here. Now people understand. Now people understand. This is the reaction which took place at anode. This is the reaction which took place at cathode, right? Since initially there were equal number of Cu dye positives and SO4 dye negatives, due to which the solution was electrically neutral. Now what happened? One of the Cu dye positive collided with the rod, took 2 electrons from the rod, got converted into Cu solid. This Cu solid will start depositing on the rod. This Cu solid will start depositing on the rod, right? And in the solution, Cu dye positives will be less now, because Cu dye positives are undergoing reduction, getting converted into Cu solid, and that Cu solid is getting accumulated on the rod, right? Due to which the number of Cu dye positives in this solution will keep on decreasing, due to which negative charge will develop in this container. Due to which negative charge will develop in this container, right? That's something which is going to happen, correct? Okay. Now guys, have a look. When continuously these zinc atoms will undergo oxidation and Cu dye positive ions will undergo reduction, the electron accumulation on this rod will continuously take place, right? A stage will reach when this positively charged rod, is going to attract the electrons from this anode towards itself, right? So can I say there will be a stage, when there will be movement of electrons, when this positively charged rod is going to attract the electrons from anode, right? Can I say a stage will reach when electrons are going to start its movement from anode to cathode, right? So is it just the movement of electrons from anode to cathode, or this is the directional movement of electrons? This is the movement of electrons in a particular direction, and movement of electrons in a particular direction, it leads to the generation of current, right? So first of all, the first point which I would want you guys to take a note of, what is going to be the direction of electrons? It is from anode to cathode, right? See, it's not only the movement of ions, it is the directional movement of ions, right? It is the directional movement of ions. It is the movement of ions in a particular direction, right? From anode to cathode. If electrons are moving from anode to cathode, what is going to be the direction of current then? The direction of current is going to be opposite to the direction of electrons, right? Yes? The direction of current will be the opposite of the direction of electrons. So the direction of current will be from cathode to anode. So the direction of current will be from cathode to anode, right? Absolutely. Now guys, have a look. See, at anode oxidation is happening. This zinc electrode is undergoing oxidation. The atoms of which this zinc rod is made, those atoms are undergoing oxidation. And those zinc atoms are getting converted into Zn di positives. And those Zn di positives are entering into the solution. So can I say the thickness of this zinc rod will keep on decreasing with time? Absolutely. The thickness of the zinc rod, since the zinc rod undergoes oxidation continuously, right? So I'll say the thickness of the zinc rod will keep on decreasing with time. Yeah? Since copper is continuously getting deposited on this copper rod, so the thickness of the copper rod will increase with time, right? Yes? Right? So I'll say, Divakar, that is something which is as per sign conventions, right? I hope you have studied electric current and physics. Thickness of copper rod, it keeps on increasing with time, right? Thickness of copper rod, it will keep on increasing with time, correct? The first point, the movement of electrons is from anode to cathode. The direction of current is from cathode to anode, right? As per the sign conventions. The direction of current is just the opposite of direction of negative charge, right? Now, the thickness of anode will keep on decreasing. The thickness of cathode will keep on decreasing, yeah? Right? Now, what is the next point? Have a look. Have a look, guys. When the first zinc atom undergoes oxidation, it gets converted into Zn di positive. That Zn di positive enters into the solution, right? That Zn di positive enters into the solution. And similarly, when first Cu di positive undergoes reduction, right? Cu di positive gains 2 electrons from the rod, gets converted into Cu solid. That Cu solid gets deposited on the rod, due to which negative charge comes into the solution. Once the positive charge enters into the solution, at the same time, SO4 di-negative will come from salt bridge and will make this solution electrically neutral. At the same time, SO4 di-negative will come from salt bridge and will make this solution again electrically neutral. Similarly, when this negative charge will be getting generated over here, at the same time, K positive ions from this salt bridge will enter into this solution and will make the solution electrically neutral, right? So what is the function of this salt bridge over here? The first function of the salt bridge is to complete the internal circuit. That's something which you all must be knowing. What is the second function? Second function is to maintain the electrical neutrality in both the containers, right? In both the containers, electrical neutrality is to be maintained by the salt bridge, right? Because the salt bridge contains the ions K positive, SO4 di-negative. Once there will be positive charge in this container, due to the presence of extra Zn di positive, which comes due to the oxidation of zinc atom from the rod, at the same time, SO4 di-negative enters into the solution, makes it neutral. Once negative charge gets developed in this container, at the same time, K positive ions will enter into this solution, make the solution electrically neutral, right? Yes? Okay. Now people, what is the function of the salt bridge over here? I'll say the first function of the salt bridge is to complete the internal circuit. complete the internal circuit. What is the second function of the salt bridge? It maintains electrical neutrality. It maintains electrical neutrality in the solutions, right? Right, people? Exactly. Now, since this is the reaction taking place at anode, this is the reaction taking place at cathode, right? Let me try to add these two reactions. Let me get the overall reaction, let me get the net reaction which takes place in this complete cell. The net reaction which takes place, right? The net reaction. How do I get the net reaction? I'm going to add these two reactions. But I'm not going to add these two reactions unless the electrons are same on both the sides. Since the electrons are both on same the side, the electrons are same on both the sides, so I'll be directly adding these two reactions. And once I'll be adding these two reactions, I'll get the net reaction as zinc solid plus Cu dye positive aqueous. It gets converted into Zn dye positive aqueous plus Cu solid. This is the net cell reaction which is taking place. This is the net cell reaction which is taking place. How many electrons got cancelled over here? 2 electrons got cancelled. So remember, this N is equal to 2. It represents the number of moles of electrons which are being exchanged from anode to cathode. This N represents the number of moles of electrons which are being exchanged from anode to cathode, right? See, the moment of electrons is from anode to cathode. So this N represents the number of moles of electrons which are exchanged from anode to cathode, right? So 2 moles of electrons are being exchanged from anode to cathode. Yeah? Okay? I'm sure every single thing is clear till here. Yeah? The first point, in case of the Daniel cell, you saw exactly chemical reactions are taking place. Spontaneously, on their own chemical reactions are taking place, correct? At anode, spontaneously oxidation is happening. At cathode, spontaneously reduction is happening, due to which electrons are moving from anode to cathode, which leads to the directional movement of electrons. And the directional movement of electrons, it leads to the generation of current. So this cell is basically converting your chemical energy into the electrical energy, right? This cell is basically converting into your chemical energy into the electrical energy, yeah? So this is how your Daniel cell works. This is how your Daniel cell converts chemical energy into electrical energy, right? Now there are a few more points which you need to take note of, right? What are those points? Have a look exactly. Have a look exactly. We say, let me erase all this. We say, just a second. We say the salt bridge avoids liquid junction potential. We say the salt bridge avoids liquid junction potential. What does that mean? What does that mean, salt bridge avoids liquid junction potential? Let's see exactly what that means. Have a look, guys. For example, this is the bigger container which I'm taking. And I'm dividing this container into 2 equal parts by means of a semi-permeable membrane. This is the semi-permeable membrane which I have over here. I've divided this container into 2 parts, right? By means of the semi-permeable membrane, correct? In this chamber, I've kept zinc sulfate solution, ZnSO4. That means in this chamber, you'll be having Zn dye positive ions and SO4 dye negative ions. Equal number of Zn dye positives, SO4 dye negatives. So this solution is electrically neutral, right? This solution is electrically neutral. Similarly, guys, if I talk about this part of the container, if I talk about this chamber, let's say this chamber contains CuSO4, right? That means Cu dye positive ions, SO4 dye negative ions. Let's assume in this part of the container, there is zinc rod, and in this part of the container, there is copper rod. And I'm connecting them externally by means of a voltmeter. This is the voltmeter with which I'm connecting them externally, right? See, these 2 electrodes are connected externally as well as they are connected internally, right? Currently, I have not used the salt bridge. If I won't use salt bridge, what is going to happen? At anode, oxidation will happen, or at anode, oxidation will take place, right? Zinc will start getting converted into Zn dye positive. That Zn dye positive will go into the solution, due to which this solution gets extra positive charge, right? Over here, Cu dye positive will undergo reduction. That Cu dye positive will collide with the rod, will take electrons from the rod, will get converted into Cu solid, due to which that Cu solid gets deposited on the rod. And on this solution, negative charge will be there, right? So positive charge on this part of the container, negative charge on this part of the container. So can I say these 2 charges are going to attract, and these 2 charges are basically going to accumulate. These 2 charges are basically going to accumulate at this junction. positive, negative. Similarly, due to the oxidation of one more zinc atom, one more Zn dye positive will enter into the solution. So one more positive charge will enter into the solution. Similarly, due to the reduction of Cu dye positive, again negative charge will enter into the solution, and that positive and negative will keep on attracting, and they will start attracting, and they will be getting accumulated at this junction. So if you look at this junction, can I say a new potential difference got created at this junction? We call this junction potential, this potential difference which got created at this junction, we call it as the liquid junction potential. We call this as the liquid junction potential. Now we will, in order to avoid this liquid junction potential, basically we introduce a salt bridge. What this salt bridge is going to do? Once the positive charge enters into this solution, at the same time from the salt bridge, SO4 dinegative will come, will make the solution neutral. So there won't be the generation of the positive charge in this chamber. Similarly, as soon as the negative charge introduces into this container, at the same time K positive will come from this salt bridge, will make the solution neutral. Due to which there won't be any generation of positive and negative charge in the two containers. If there is no generation of positive and negative charge in both the containers, right, there won't be any sort of potential difference getting created at the junction, right? If there are no charges getting created in the chambers, if the charges are not getting created, right, that means the charges are not going to attract. That means at the junction there won't be any sort of potential difference. So can I say your salt bridge is going to avoid the liquid junction potential, right? This is the main use of the salt bridge, to avoid the liquid junction potential. I'm sure it's clear to everyone, right? Okay. Exactly, Ritika. It avoids the liquid junction potential. Yes? Right? Now comes few more points. Let's talk about those few more points. About this. Okay. People, if you remember, what was the net cell reaction which took place in this cell? The net cell reaction was zinc solid plus Cu dye positive aqueous gets converted into Zn dye positive aqueous plus Cu solid. This was the net cell reaction, if you remember, which takes place in this cell, right? This was the net cell reaction. People, in this net cell reaction, do you see the ions of the inert electrolyte participating? No, right? The ions of the inert electrolyte are not participating in this net cell reaction. So first of all, that electrolyte whose ions does not participate in the net cell reaction, that's what I call as inert electrolyte. That electrolyte whose ions do not participate in this net cell reaction, I'll be calling that as the inert electrolyte, right? So these K positives, SO4 dinegatives, you're not seeing any K positive or SO4 dinegative in the net cell reaction, right? So these ions of the salt bridge, right? These ions of the inert electrolyte, they have not participated in this net cell reaction. Yes? So any electrolyte whose ions do not participate in the net cell reaction, we call that electrolyte as the inert electrolyte. Point number one, right? Okay. The main and important thing for the inert electrolyte, its ions should not participate in the net cell reaction. Its ions should not participate in the net cell reaction. Point number one. Point number two. Ionic mobility of both the ions. Ionic mobility of both the ions should be the same. What does that mean? That means the speed with which SO4 dinegative enters into this solution, same should be the speed of K positive to enter into this solution, right? The speed with which both the ions move in the opposite direction should be the same, right? Then only the liquid junction potential won't get created. Then only the solution will become electrically neutral, right? Yes? Okay. So this was all about what? This was all about the Daniell cell, its working, how it converts chemical energy into the electrical energy, how cell reactions take place spontaneously, right? And due to the spontaneous cell reactions, how the movement of electrons happens from the anode to cathode, yes. How the movement of current is from cathode to anode, right? The thickness of this cathode keeps on increasing, thickness of this anode keeps on decreasing, right? Yes. What is the use of the salt bridge to maintain to complete the internal circuit? Point number 1. Point number 2, to maintain the electrical neutrality. Point number 3, to avoid the liquid junction potential. Yes. So all these things we have discussed in detail, right? Now, the point is how these galvanic cells are represented. How these galvanic cells are represented, correct? So let me talk about something called as the representation of the galvanic cell. A representation of the galvanic cell. See guys, it's simple. I'm going to draw two lines which represent basically the salt bridge. These two lines represent the salt bridge, right? On the left hand side of the salt bridge, I'll be always writing the anode. On the right hand side of the salt bridge, I'll be always writing the cathode. Okay? Now, if I need to represent which cell? The Daniell cell. How will I be representing it? See guys, what was first of all the net cell reaction in the Daniell cell? The net cell reaction was like this: zinc solid plus Cu dye positive aqueous, it gives Zn dye positive aqueous plus Cu solid, right? This was the net cell reaction which used to take place in the Daniell cell. Now I'm going to represent the Daniell cell from this net cell reaction. And how am I going to represent it? Have a look. Oxygen instead of zinc, 0. Copper plus 2. This zinc plus 2. This copper, 0. 0 to plus 2, increase in the oxidation state is something which I call as oxidation. So zinc is undergoing oxidation. And oxidation takes place at anode. So zinc electrode is your anode. Plus 2 to 0, decrease in the oxidation state is what I call as reduction. So Cu dye positive is undergoing reduction. And reduction takes place at the cathode, right? Have a look now. In the middle, I'll be drawing two lines which represent the salt bridge. On the left hand side, I'll be writing the anode. At anode, oxidation takes place. And oxidation of zinc is taking place. And zinc is getting converted into Zn dye positive. So zinc solid getting converted into Zn dye positive, right? Yes. And this Zn dye positive enters into the left container. Let's assume the concentration of Zn dye positive in that left container, in the anodic container, is C1, right? On the right hand side of the salt bridge, I write the cathode, and at the cathode, reduction takes place. Reduction means gain of electrons, right? So this Cu dye positive is undergoing reduction. Cu dye positive, which was basically in the right container, in which the concentration of Cu dye positive was C2, for example, it gets converted into Cu solid. This is how you represent your Daniell cell. This is how you represent your Daniell cell. Yeah? This is how you represent your Daniell cell. Okay, let me give you a few more representations of the galvanic cells. Or let me make the heading over here. How to represent a cell from its net cell reaction. From its net cell reaction. How to represent a galvanic cell from its net cell reaction. Understand properly. Let's say I have got a galvanic cell, correct? In which the net cell reaction is, for example, like this. Have a look. Let's assume the net cell reaction is like this. Zinc solid plus Cd dye positive, cadmium dye positive aqueous, getting converted into Zn dye positive aqueous plus Cd dye positive. Plus Cd solid. Plus Cd solid. This is, for example, a net cell reaction which is taking place in some galvanic cell. I need to represent it. How will I be representing it? First of all, oxygen instead of zinc, 0, cadmium plus 2, this zinc plus 2, cadmium 0. See, 0 to plus 2, increase in oxygen state means oxidation. So zinc is undergoing oxidation. So zinc is behaving like the anode. Similarly, Cd dye positive, getting converted into Cu solid, decrease in the oxygen state means reduction. Reduction takes place at the cathode, right? So this cadmium electrode is my cathode, right? How do I represent it now? Simple. Two lines in the middle, salt bridge. On the left hand side of the salt bridge, I'll be writing the anode. And at anode, oxidation takes place. Zinc is getting converted into Zn dye positive. So at anode, zinc solid getting converted into Zn dye positive. And that Zn dye positive enters into the anodic container in which the concentration of Zn dye positive I'm assuming as C1, right? In the middle, salt bridge. On the right hand side of the salt bridge, cathode. At cathode, reduction takes place. Reduction means gain of electrons. CD dye positive is getting converted into CD. So CD dye positive, whose concentration in the cathodic container was C2, for example, getting converted into Cu solid. This is how you represent this cell. This is how you represent it. Yeah? Isn't it simple, guys? Yeah? Isn't it simple? Right? Okay? Exactly. Let me take few more cases so that you can understand it properly. For example, I'm writing one more cell reaction. Let's assume I'm writing one more cell reaction. A cell reaction of some galvanic cell. I need to represent that, yeah? The cell reaction is like this. H2 gas plus Cu dye positive aqueous getting converted into 2 times H positive aqueous plus Cu solid. This is a net cell reaction of some galvanic cell, correct? Let's represent this cell. First of all, H2 is undergoing oxidation and Cu dye positive is undergoing reduction. If this is undergoing oxidation, so this electrode is going to behave like the anode and this electrode is going to behave like the cathode. Copper electrode is going to behave like the cathode, right? So first of all, these two lines, they're going to represent the salt bridge, right? On the left hand side of the salt bridge, I'll be writing the anode, right? And at anode, H2 is getting converted into H positive. So I'll be writing H2 gas getting converted into H positive, which enters into the left container, anodic container, in which the concentration of H positive is, for example, C1. On the right hand side, I'll be writing the cathode. At cathode, reduction takes place. Cu dye positive getting converted into Cu solid. So Cu dye positive, whose concentration in the cathodic container was C2, getting converted into Cu solid, right? But one more thing. Since it's a gaseous electrode, right? Whenever you see a gaseous electrode, you write platinum with it, okay? Why you write platinum with it? There's a reason for it. When I'll teach you how to make the hydrogen electrode, at that time exactly I'll show you why this platinum is written on this side, okay? So right now you just remember one thing. Whenever you see a gaseous electrode, on that side you'll be writing platinum with it, okay? Platinum, comma, H2 getting converted into this, right? This is how you represent the galvanic cell whose net cell reaction is this one, yeah? A last example I'm going to take, and with that I'll be ending the tonight's session, right? And I'm sure you can. Okay, this is something which I'm going to give you as the homework, right? This is something which I'm going to give you as the homework. For example, you have got the reaction like this. Let's say it is 2 times Ag solid plus CD dye positive aqueous gets converted into 2 times Ag positive aqueous plus CD solid. This is a net cell reaction for some galvanic cell. You need to represent it, okay? And let me know, show me the representation of this galvanic cell in the comment section once the video ends, right? Okay? Do let me know in the chat box, guys. Not in the chat box, sorry. In the comment section, how to represent this cell exactly. Yeah? I'll be waiting for your answers. So I think this much is enough for the tonight's session, right? This was just the introduction of everything. Introduction of the Daniell cell, how Daniell cell works, what are the main points there in the Daniell cell, right? And people, there's a link in the description about the Telegram. Do click on the link, get added to the Telegram group and stay updated about the classes. The ones who have not liked the video yet, do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. And one more thing, guys, I would like to tell you. That is regarding the pro subscription, right? So if you are preparing for JEE 2022, you can join our actual Vedantu platform, our actual Vedantu classes apart from the YouTube sessions, right? I'm talking about the actual Vedantu classes, which takes place on the actual Vedantu platform, right? For that, what you need to do, see guys, this is the video which you guys are currently watching. Just drag the video a little down, click on this show more. After clicking on this show more, you'll be getting a lot of links. See, maximum students currently are looking for CBSE Term 1 crash course currently, correct? So if you're also looking for CBSE Term 1 crash course, you need to click on this link. This link, after clicking, you'll be getting two things: light program, classic program. Choice is all yours to take. I mean, it's going to be your wish to take any of the plans, right? If you want CBSE Term 1 crash course on the actual Vedantu platform by the teachers of your choice, let's say you're taking this light plan, okay? You need to use the coupon code WPPRO and click on this buy complete course, give your number, give your email ID, on which you get the OTP, and you get automatically enrolled into the batch in which we are doing the CBSE crash course on the actual Vedantu platform, right? Okay. And at the same time, if you are looking for a JEE dropper program, right? For the ones who just dropped in the recent JEE, we have got two plans for you. One is your light plan, one is classic. You can be with us for complete 1 year, right? This is the course fee for complete 1 year, and no need to pay this much amount in one go. You can pay this much amount in installments. Or if you are new to Vedantu, you have no idea how the actual Vedantu looks like, you can try it out for a month. See if it is working for you. Just try it out for a month, right? Just give your number, everything, okay? You'll get enrolled in that. And people, if you are looking for, if you are going to appear in JEE in 2022, if you are right now in class 12 and you want to currently prepare for the JEE 2022, click on this link. After click on this link, again you'll be getting two plans, right? These are the two plans, and these are the course fee for the 1 year classroom program which you are going to be with us, right? And no need to pay this much amount in one go. You can pay this much amount in installments. And again, I'm telling, if you are new to Vedantu, if you have no idea how the actual Vedantu platform looks like, right? How the actual Vedantu platform works, you can click on this, try for 1 month. You can try this plan for a month, get enrolled into the batch for a month, see if it is working for you, then you can go for the complete 1 year program, right? The choice is all yours. And trust me, you're going to love it if you're going to enter into the actual Vedantu platform. The procedure is same. Use the coupon code WPPRO, right? Click on this, put your number, put your email ID, you'll automatically get in, right? And if you've not liked the video yet, please do like the video, share the video with friends, and do not forget to subscribe to the channel as well, okay? So with this, people, I'm taking a leave. So I'll see you guys tomorrow again at the same time. Tomorrow we are going to talk about the standard EMF. We are going to talk about the electrode potential and everything, right? Yes. So take care. Bye-bye. God bless you all and love you all, guys. Take care. Bye.